Good morning. So today we are starting our next unit over the atoms in the periodic table. So this past week we had spent time talking about whether something would be classified as a element, compound, or molecule. And we had said that all matter is made up of atoms, right? And so right now we know that there are 118 different elements that we have documented and recorded on our periodic table. Now, could there be many more than that? Yes. We have created a lot of elements through lab procedures, through the process of bombarding atoms with protons and seeing if those protons end up sticking, things like that. A lot of things have been changing in terms of matter. What is matter, what is not matter. The idea of dark matter, whether we'll be able to actually detect dark matter and see its influence, because we know it does have an influence on objects around it. It does exert a force of gravity, but we can't necessarily see it. So still limitations when it comes to our understanding about all matter and things like that. But a lot of our understanding came all the way back in Greek times, when we had our first philosopher named Democritus. Democritus was a philosopher who kind of started thinking about matter and said, well, if I take a rock and I keep cutting it in half and in half and in half and in half, eventually I'm not going to be able to cut it in half, and it will no longer be identified by its properties. And that's where the very first word atom came from, because it described something that was indivisible, that we couldn't cut it in half anymore. Well, you guys actually know we can split atoms, and that's actually how we get an atomic bomb. So an atom is our smallest particle, which an element can still retain its properties. So we talked about this past week. Aluminum, the element, is made up of aluminum atoms. The atoms we cannot actually see because the atoms are so small. But what they did is they were able to shoot a lot of different particles at those atoms in order to kind of figure out what the atom looks like, and then also whether or not it was positively charged or negatively charged, because it's going to move according to that. So our atom, if we look at the very, very center of our atom, that is what we call the nucleus. In the nucleus, we have both protons and neutrons. Protons are positively charged. Neutrons are neutral. So if that says neutral, that means there's no charge. Surrounding that nucleus is what we call an electron cloud. We tend to put those electrons in orbitals, but we don't necessarily stay in those orbitals. They're not fixed there forever and ever. But this region is negatively charged. Now, you guys would probably be able to tell me that two positives, opposites attract, but likes repel. So if I have two positives by each other, they would repel. So if you think about our nucleus, in our nucleus we have a lot of positively charged particles. So our nucleus, this is kind of a weird idea, because the nucleus, which is really, really dense, and it has lots and lots of positively charged protons, opposites attract, but likes repel. So if I have positive by positive in my nucleus, I know that it's not going to want to be by each other. So you might be wondering, well, why does that actually happen? Well, that's because we have what is called a strong nuclear force. A strong nuclear force kind of holds together that nucleus. So it creates like an attractive force with our protons and neutrons and kind of glues it as one. So we do have some of those forces playing a role in the structure of the atom. When we get atoms that are way too big, when they have protons exceeding 83, you tend to see that strong nuclear force cannot overcome the repulsion between our protons. So sometimes we do have atoms that are going to decay. Sometimes we do have atoms that do not exist out in nature naturally. We only have 92 naturally occurring elements. All the rest are going to be man-made or do not exist long enough for us to detect out in nature. So with our atom, big thing, very center, we have our nucleus. In that nucleus, protons and neutrons. Surrounding the nucleus in our electron cloud or in our orbitals are going to be our electrons, which have a negative charge. So that proton, again, it is positively charged. We give it a mass of 1. Our neutrons are neutral. We give it a mass of 1. But our electrons, who are negatively charged, is really, 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 I wish I could say really 30 more times, small. So since it's super, super small, we actually assign a mass of 0. The electron does not really contribute to the overall mass of the atom. So for the most part, we say it attributes 0 AMUs, or atomic mass units. So again, we have all of our different elements. You guys are going to be responsible for learning the first 20. So make sure you do start learning those. We'll have a quiz next week. It'll be a quick little 10-minute quiz. Can you match up? Hydrogen goes with H, nitrogen goes with N, carbon goes with C. So those are our elements 1 through 20 on our periodic table. There is a Quizlet that you can start practicing with as well. So then you are good to go, and we'll have a nice perfect going into the grade book. All right, so our elements, if we look at our different elements on the periodic table, each element has a different atomic number. The atomic number is equal to my number of protons. If my atom is neutral, so that means the number of electrons is equal to the number of protons, then my proton number is the same as my atomic number as well. So for right now, my atomic number is both my protons and my electrons. So each element, we have the name, we have a symbol, we have atomic number, and then we also have mass number as well. So up at the top, you can see in that element square, the element name spelled all the way out. We do symbolize it with 1 or 2 letters. Remember, a different element will be symbolized with a different capital letter. So remember, 1 capital letter per element. If that was a capital C, a capital L, then that would actually be 2 different elements. Whereas here, capital L, lowercase, or capital C, lowercase l, that is just 1 element. The larger number, which is not necessarily always on the bottom of our element square, is going to be the number of protons plus neutrons. So remember, we had said that electrons are so tiny that they do not contribute to the overall mass of the atom. That is why that number on the bottom is just protons plus neutrons. So this number here, protons plus neutrons, this number is going to be the same as my number of protons and my number of electrons. So for chlorine, I have 17 protons, 17 electrons. In order to figure out how many neutrons I have, though, I know I have 17 plus N equals 35. So if I go through and I try to solve for that, hopefully you guys can tell me subtract 17 on both sides. And you're going to get that your number of protons is equal to 18. Okay, so we can go through, solve for the number of protons, neutrons, electrons, and then be able to calculate mass number or atomic number based upon what information is actually given to us. The periodic table, this is kind of where we're going to be focusing next week on. But remember, you do need to know the first 20. So if you look, these are going to be all your ones that are part of the first 20. Okay, so hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, potassium, and calcium. So start learning those first 20. First 20 are important. Biggest thing, if you look, the top number, which is our atomic number, is all different. Remember, they each have a different number of protons. That's what makes them unique. That's what makes them different from other atoms. That's why gold is different than silver, because the main difference is that number of protons. So again, just a big capital or recap for you guys. On that periodic table or on an element square, you're going to see up at the top the actual name of the element. You'll see its symbol. you'll see the atomic number, which is 17. And for right now, our atomic number is always going to be equal to the protons and electrons because they are going to be equal. And then down at the bottom, my mass number is protons plus neutrons. So this is protons plus neutrons. So up about a slide or two ago, when we solved for that number of neutrons, we took the mass number and subtracted the atomic number. So we did big number minus little number gave us number of neutrons. All right, so if I'm looking at this one, I notice that here my element is hydrogen, the symbol is H. I see at the top, there's my atomic number, which is 1. So I have 1 proton, and I also have 1 electron. Now, something that's weird about hydrogen is if you look, here's my mass number. Well, my mass is protons plus neutrons. Well, if my mass is 1, 1 equals 1 plus what? So if you notice, my number of neutrons here is going to be 0. Hydrogen sometimes exists with no neutrons, 1 neutron, or 2 neutrons. So if we have different numbers of neutrons, that is what we actually call an isotope. An isotope is going to be an element with different numbers of neutrons. Still the same number of protons, but neutrons can change. So we can sometimes have 0, 1, or 2 for hydrogen. So that is possible. So isotope, we would have different numbers of neutrons. All right, so looking here, my element is oxygen. My symbol is O. I have an atomic number of 8 and a mass of 16. Well, since my atomic number is 8, I know my protons and electrons are both 8. In order to get neutrons, though, I need to know that my mass is equal to my protons plus neutrons. So to solve for my neutrons, I'm going to take my mass minus protons. So 16 minus 8, and that's going to give me 8. Our next example, I have iron, which is symbol Fe. Protons, same as my atomic number, so 26. Since they are neutral atoms, I have 26 electrons. So I have 26 positives and I have 26 negatives. So those cancel out and give me a neutral atom. Now to get number of neutrons, you're going to have to take 55 minus 26. So when you take that 55 minus 26, hopefully you guys can do that really quick, you are going to get 29. So 29 neutrons, 29 neutrons. All right, nitrogen, symbolized by the symbol N. Atomic number is 7, so remember that means I have 7 protons, 7 electrons. And then to solve for neutrons, I have to look at the mass and do mass minus protons. So 14 minus 7, hopefully you guys can do that pretty quick, would be 7. Au is gold. If you look, gold, atomic number 79. So if my atomic number is 79, that means I have 79 protons and 79 neutrons, 79 protons, 79 electrons. In order to get neutrons, I need to take my 197 and subtract 79. A lot of students just remember big number minus small number, and you're going to get 118. All right, so remember I had said on your element cards, the big number is not necessarily always at the bottom. There is a way that we can write an element in chemist shorthand. So with chemist shorthand, if you notice, I have the symbol right there. B stands for boron. At the top on the left, I am going to have the mass number. On the bottom, I'm going to have the atomic number. So if I was to write carbon, carbon has a mass of 12, but an atomic number of 6. So my atomic number is always going to be the smaller number. That is always going to be the number of protons. And for now, the number of electrons as well. Okay, so if I'm looking at this version and say that I was given, let's say nitrogen 15 atomic number 7, I would have to go through and say, okay, protons, neutrons, electrons, which remember protons are positive, neutrons are neutral, electrons are negative. My atomic number is always the smaller number. So I have 7 protons, 7 electrons, because remember, protons, neutrons are going to be the same for right now, because I have neutral atoms. And then 15. So I don't have 15 neutrons. In order to find neutrons, I need to take that mass, which is 15, and subtract the number of protons, which was 7. And then I would get my 8. Okay? So you'd follow the exact same process as you did here on the ones above. It's just now it's written a little bit different for you. It's just a different way that scientists actually denote their different elements. Okay? Alrighty, that is it for today. Good job, Dice. Thank you.